Okay, let's take a look at this homework problem, and I'm going to attack this through a slightly different lens. I'm going to give you some tips on how to determine which molecules are polar. First off, I know that this question asks you to consider the VSEPR geometry and the overall shape name. I'm going to give you a couple tips because you're likely to see some of these concepts in multiple choice on either a period test or on the final exam, and I want to make sure that you can do them efficiently and correctly. So let's take a look at this set of molecules, which was provided in your homework, and see if we can determine which molecules are polar with some simple concepts that maybe will save you some time in the sense that you don't have to draw out the VSEPR structure. So remember, and that's a key point that I want to emphasize, you can always determine whether or not the molecule is polar by first drawing the Lewis structure, then going to the VSEPR geometry and drawing the bond dipoles and seeing if they cancel. But remember, we have a couple of axioms that we developed in the textbook, and one is that molecules that have different outer atoms are always polar. So right off the bat, I can argue that HCN, because the outer atoms are different, hydrogen is obviously not nitrogen, and CH2F2 will be polar because they have different outer atoms. So if this was a multiple choice question, I know immediately that these two are polar. I don't have to do anything else. I also told you in the textbook that hydrocarbons, namely compounds that just have carbon and hydrogen, are always nonpolar because the only possible bonds you can have are carbon-carbon and carbon-hydrogen, and by definition, those bonds are always nonpolar. So methane, CH4, must be nonpolar, and we're going to ignore that in our analysis if this were, a multiple choice question. We can't really say anything about BF3, beryllium dichloride, sulfur dioxide, PF3, and SCl2 yet because we need to draw the Lewis structure and see if they have a lone pair. So this will take a little more time. There's not much we can do about that. But remember that molecules that have lone pairs will be polar. So I provided the Lewis structures here. Remember that boron and beryllium are exceptions, and sulfur can have an expanded octet. But notice here that sulfur does have a lone pair in SO2, while the boron does not. So we would anticipate that this BF3 is nonpolar, while the SO2, PF3, SCl2 will be polar because they have lone pairs. So this is a quick way to determine polarity without having to draw the VSEPR geometry. Of course, we want you to understand that as well, and that's why we asked you to do that for this problem. But you don't have to draw any arrows. You can kind of use these tricks to determine which molecules are polar and which molecules are nonpolar. Okay, so let's move on to doing the VSEPR geometry because that was also part of this problem. And we're going to start with the AXE notation for each of these molecules, which I provided here. Couple of points that I want to note. The AXE, the X refers to the outer atoms, and the E is the number of lone pairs. And again, we're talking about pairs here, not number of electrons on the center atom. Double bonds and triple bonds are ignored, so this would be AX2E1 because the sulfur is connected to two oxygen atoms and it has one lone pair. Here's another example. Sulfur has two lone pairs, so it would be AX2E2 because two outer atoms. Overall, it shouldn't be too complicated to generate this notation. Translating this into a VSEPR structure can be a little more challenging. I basically remember the electron group geometries, which are the basic structures, and then remember that we name the structure as if the lone pair doesn't exist. So and we're looking at the first four here, BF3 is AX3. It has three electron groups, three things that it has to separate in space. And it's the electrons in these bonding pairs, in case you were wondering. And the best way to do that is trigonal planar with a 120-degree bond angle. Again, if we didn't remember any of the tricks, we could always draw bond dipoles. We recognize that these are polar bonds in the plus end, and I know this isn't the best drawing, but it's what I had. This should be sort of the arrow here should come out a little bit more, so it's almost like a plus sign. That points or starts at the more electropositive element and goes to the more electronegative element. And if you think about this, if you're the boron atom and you're being pulled by three identical fluorine atoms with equal force in the direction of a triangle, you're not going to go anywhere, and that's why we say that BF3 is nonpolar because its dipole moment is zero. All the bond dipoles cancel out. Let's move to SO2 because I think that's a little more interesting. SO2 has an electron group geometry of trigonal planar. It has 3 electron groups, so anytime you have 3 electron groups, it's based on the trigonal planar structure. However, we name the structure as if the lone pair wasn't there. So we kind of ignore this lone pair when we name it, and this structure is known as bent. The angle is, of course, based on a trigonal planar like geometry. It's going to be less than 120 because this lone pair compresses this bond angle. Again, suppose we didn't remember that molecules with lone pairs are polar. We can draw the arrows. If you're the sulfur atom being pulled downward here by 2 oxygen atoms, you're going to go this way. You're sort of going to go towards the bottom of this page, and that's kind of the idea of vector addition, which we haven't covered, and I like to think of it as basically tug of war. So here the sulfur will move, the arrows don't cancel, and the molecule is polar. All right, let's move to the last 4. Just to note a couple of things here. PF3 has 4 electron groups. It has an electron group geometry of a tetrahedral-like structure. Again, so there's a difference between electron group geometry and the molecular geometry or shape. So we have a tetrahedral-like structure here where the wedge is coming out of the plane and the dash is going into the plane defined by the paper. We name the structure again, though, as if the lone pair didn't exist, so it's trigonal pyramidal. The arrows don't cancel out, and the molecule is polar. HCN, again, different outer atoms can be linear. It's an AX2 system. However, there's only one bond dipole here. The CH bond isn't polar, and clearly the arrows don't cancel, so this is why it's polar. And let's come down and look at CH2F2. This is a molecule that is tetrahedral. It has 4 electron groups, so the electron group geometry and the molecular shape are both tetrahedral. But here, there are only 2 polar bonds. So if you imagine you're the carbon atom being pulled in 2 directions of tetrahedral shape, not in the other 2, you're going to move sort of this way. Up and to the right. So that's why this molecule is polar, and it has a tetrahedral shape with a bond angle of 109.5. Good luck.